Okay, everyone. One more lesson from this book, Chapter 14, Graph Theory. I took the graph that we had yesterday, or last lesson, and notice how I changed it. I put numbers on all of these edges, okay? When you have a graph with numbers on all these edges, it's called a weighted graph. Each of the edges has a weight, okay? We also already talked about colored graphs. There's also directed graphs where you can only go one direction or the other. So there's lots of different ways to modify graphs in order to organize and show relationships. What can you do with numbers? Why would you want to have numbers on graphs? I'm going to show you two different reasons that basically fill out the rest of chapter 14 in the book. I'm going to do them in the opposite order, but they're both there. Suppose that these are all houses for these various students, all live in their own home with their families, and suppose this particular neighborhood wanted to have internet connect all the houses together, okay? So if you have a bunch of things that are connected with internet, this would be something like this, would connect all of these vertices, and maybe you have another one like this, and maybe another one like this, and maybe another one like this, and maybe another one like this. So they would all get the internet from whatever the source is. It doesn't matter what the source is, the internet would go to all of those different houses. Notice that what you don't need, if all you're trying to do is connect them for internet, you don't need anything like this. Okay, that's called a circuit, where you can go around and return back to your starting point. Okay, your starting vertex. No need for that because there's only one path that you need to get to any particular vertex. So this is called a tree when you connect things like this without having any circuits, any thing like that. And we want a spanning tree. A spanning tree is a tree that connects all the vertices, okay? Not just some of them, but all of them. So that's what we're after. And usually when you have a spanning tree, especially if it's a weighted graph, you want a minimum spanning tree, a minimum cost. Minimum cost or minimum spanning tree, meaning you want it, if this is how much money it costs to connect each of these houses, you want to get them all connected. You want to get them all connected in a tree, but with a minimum total cost. So how do you do it? There's an algorithm called Kruskal's algorithm, which basically says you do kind of the natural thing. You start by saying, well, we want the cheapest routes possible. So here's a 2. It only costs whatever 2 stands for, $2 or $200 or whatever, to make that connection. So we want that. And then you just work your way up. Here's a 3. So we'll take that one. And here's a 4. So we'll take that one. Here's a 5 and here's a 5. I guess we can use them both. So we'll take that one, and also take that one. Notice we're connecting all these vertices. Here's a 6, but I don't want to take that because notice if I have that 6, I've got myself a circuit. There's no need for it. I've already got these 3 connected. I don't need, that's redundant to have that one. Same here. I don't need this 6 because I've already got this one, and this one connected. There's no reason to have this. So we skip those and we go on to the next one. So you just keep going from the smallest to the largest, just making sure that you don't get any closed. Whoa, wait a second. I've got a closed circuit here, don't I? See that? Whoa. See that? So here's a 2, 3, 4, 5. I've got myself a circuit here. I just noticed that. So I could get rid of either one. Let's just keep this one and leave that one undone. Okay? So good. See that? So I don't want that 5 because that 5 would have given me a whole circuit. Again, I don't want this 6 and I don't want this 6. So now, how about 7? If I grab 7, now I think I've got connected all of the vertices and I don't have any circuits. I certainly don't have any circuits, and all of them are connected. So from any one I can get to the other. So that's a kind of a typical nice graphing problem. As I say, I like to just think of where it's used. It's used if you want to connect them with internet and you have this tree. What's the tree look like? The tree looks like this. And so that's kind of what you've got, right? You've got all the branches of the tree there. So that's called a spanning tree. Okay, so that's that. What would be another place where you would make use of these weights? So let's get rid of the, unless you can just ignore them. I guess maybe we better kind of get rid of them here. Okay, so there they are again. What would be another place where you'd maybe have the need for weights? What if let's say this is Ike. What if Ike wanted to visit all of his friends? Okay, these would be the sidewalks to the various houses or streets, whatever you want to think of, and he doesn't care whether he goes along every street or anything like that. He just wants to visit every house. And after visiting every house, wants to go back home again. Okay, so what might Ike do? So this is called a Hamilton circuit. Remember what a circuit is? A circuit is where, did I spell circuit right? UIT, yeah. Okay. A circuit is where you want to come back to where you began. So that's, you make a big circuit. And a Hamilton circuit is one where you visit every single vertex. Okay, you could have just a regular circuit like this, but a Hamilton circuit is one where you hit every one. So how do we do that? It turns out that this problem has no guaranteed solution. Okay, we want the minimum cost. Okay, these are the times it takes to go from house to house. We want to do it in the minimum cost or minimum time. I mean, one option would be to look at all the possibilities. Okay, look at all the possibilities, and quite often there's lots of them. And unless you do that, you basically have no guaranteed way to know that you're going to have the smallest cost. You could start by doing things kind of similar to what we did before. You could kind of take some of the lower priced ones and so on and add those, and always start here and go here, and then say, well, now I've got my 2 and my 3. Here's a 5 that gets me to this one. One way or another, I've got to go here, so I guess I probably have no choice, and then I'd have to take this one. If you wanted to return, you'd have to have another edge here going back from there to there in which you could return. If you don't have another one there, you can't go backwards. You only go along at once. And let's see, where else? Have we hit them all? Then maybe here and maybe there. Hard to say whether that's, I used up a 9. I didn't use this 4. There might have been some other path, some other circuit that was less expensive. Okay, so as I say, there's no clear way. This is an important problem because quite often you've got someone who wants to visit lots of places. It's called the traveling salesman problem. When you think of the traveling salesman as starting at his hometown and wanting to go to, in this case, a total of 10 cities, including the hometown, and then back again. And so if you look at all the possibilities, suppose that there's air flights to all these, or bus flights, whatever they are, bus rides to all these possible cities. And once you get there, once you get to this city, now you can have all these possible things. So it's a complete graph, right? Complete means that every two vertices has an edge between them. So you keep doing that. And each one of these things then would have a price to it. This might be $98, and this might be $103 on the bus, or something like that. And so the question is, if you wanted to use the brute force method and just try every single one, how many would you try? Well, think about it. If you start right here, this is a nice counting problem. If you start right here, you have 9 options for where to go. Once you go someplace, now I have 8 options. Once you go someplace else, now I have 7 options, then 6, then 5, then 4, then 3, then 2, then 1. And so I multiply that out. That's 880. Okay? Lots of options. Now actually it's just half that many, because the one that goes this direction is going to be the same price as the one that goes this direction. But even dividing that by 2, it's still going to be what, 180,000 roughly. Oh, I guess that's easy enough to do. 108,440. So you'd have that many you'd have to try. Still a lot. So that's the only way to make sure. If you don't want to spend all that time, then your only choice is just to kind of do something similar to what I did here. But just to show you that that doesn't always work, look at this graph. If we were to just start right here and go to every vertex, always taking the shortest path, shortest weight, we would go like this, and then let's see, there's that one, then we go here, then we go here, then those are all 2s, here's another 2, we'd go here, and now we'd have a 9. So 2 plus 2 plus 2 plus 2 plus 9 is 17 total. Whereas if you go a different route, you'd go like this one, which is 2, and then this one, which is 2, and then instead of going this 2, you'd go this one, which is 3, and this one, which is 2, and this one, which is 3. So it'd be 2, 2, 3, 2, 3, 2, 2, 3, 2, 3, which is 6, 7, 8, 9, 10, 11, 12. So it's only 12. See that? Should I do it one more time? If you always take the shortest route, you're going to go 2, and now you can go 2, and now you can go 2. You keep taking all the 2s. There's a 2, but now you're stuck. You got to go here now. That's your last one. So you go up to 9, and you're up to 17. Whereas if you look ahead a little bit, and you go 2, 2, and then instead of taking this 2, you take this 3 and go up here, and now down here, and now this one, you're going to get there faster or cheaper. See that? So the point is, there's no clear-cut way to solve that particular problem. Okay, final thing let's do. Let's get rid of these weights again. And let's think of one more situation which might arise when you are dealing with graphs. Let me copy it down here. That's it, isn't it? Okay. So I'll get rid of that one. Okay, so now here's what we want to do. Forgot who the person was. Let's just say whoever this person was right here. That person lost their telephone, lost their cell phone somewhere during the day, and they're afraid that they might have lost it while taking a trip to the various friends' houses. This person has been to all the friends' houses and everything and can't find it. And so they've got to take a path that it's not so important that you, well, what's important, let me say it this way, what's important is that you cover every edge. So now we're not concerned with hitting every vertex just once or anything like that, But what we are interested in is covering every edge just once, if possible, because you want to walk down the sidewalk. Once you walk down it, you don't want to walk down again. So let's see if it's possible. Okay, so starting right there, you walk down this sidewalk. And by the way, this is called Euler Circuit. Circuit again, because we want to end up where we started. And Euler, I'll show you why in a minute, why it's named Euler. So I'll go there and then go here, and you don't want to return to where, well, no, that's fine. We can go back up here, no problem. We just don't want to do any edge more than once. And, I can't see that. I'm in trouble. Because if I go here, I'm going to have to do one of these edges again. And so I can see that I'm in trouble right there. Okay, I can go here, here. I can't go down there. I can go here. But I'm in trouble. If I go down this path or this path, I'm going to have to hit an edge twice. And that's the whole point, is you only want to hit every edge once. Okay? So, so that didn't seem to work. We could have kept trying. But let me give you a couple examples of things that either will or won't work, and let's see once if we can figure it out. Here's one. Let me start with this one instead. That graph right there. This graph right there. This graph right there. Every corner is a vertex. This graph right there. This graph right here. Okay? And one more, this one right here. Okay? Well, let's see. Can I start here and hit every edge and get back to where I started? No way. Can I do it here? No, of course not. Can I do it, let's do another one. Can I do it here? Starting with one and just go down every edge and get back where I started, hitting every vertex once. No, I can't, because this is all one graph here. So we see that in order to have any hope of it happening, we have to have a connected graph. So it's got to be connected. That's for sure. How about this one? Can I do this one? Yeah, that's easy enough. Just go like that. Okay, that'll work. How about this one? This one will work. How about this one? Now I'm in trouble again, aren't I? Because I can go like this here, but I can only hit this one once. So either I stay here and I don't hit this edge, or else I go down this edge, but I can't hit the edge twice. So that one I can't. Here I have two edges from there to there. So there it is. Okay? Well, you look at these and you say, what are the ones? They all have to be connected in order to work. As I say, something like this doesn't work. Even something like this doesn't work, because you can't get from here to here. It has to be connected. But not only do I have to be connected, what else seems to be the case? What's the problem with something like this? Notice, let me draw it again. Say I start right here. Think about it. Starting from here, once I leave, I need to be able to return. Every time I leave, I need to be able to return, and I need to be able to return by a different edge. So I'm going to need an even number of edges coming to this point, because every time I take off from it, I have to come back from it. See that? I came back. Now that I came back, I take off. Well, the problem is I took off, but I can't come back again. So they almost have to be in pairs, that when you have one to leave, you have to have another one to come back to any particular vertex. See, notice that was the situation right here. See this? Here, I took off, there I came back. I take off again, there I came back. So the fact that you take off and come back in pairs means that you have an even number of degrees for each vertex. And it turns out that that's all you need, along with being connected, in order to have what's called an Euler circuit. So let's just go ahead and do a really complicated one. Do one like this, and do this, and we'll do this, and do this, and do this, and do this, and do that. Let's just see what this looks like, okay? So the key is you look and you say, what's the degree of each vertex? Here it's 1, 2, 3, 4. Here it's 1, 2, 3, 4, 5. Here it's 5. Here it's 4. And here it's 4. Okay, and we could have another one here just to make things a little more interesting. I could put this one right here and have this one be 2 right there. Okay, so there it is. Okay, so here's the key for Euler circuit again. As long as they're all even numbers, you're going to be able to have an Euler circuit. So the fact that I have odd numbers, if you have any odd numbers, you will not have an Euler circuit. So there's no way to do this one. However, if I can, it's called Eulerize. If I want to take this particular path and repeat it, even though I'm going down that path twice, then I've Eulerized it. Now I know I'll be able to do it, to get a Euler circuit on this graph. Now I'm doing this one twice, but that's the best I can do. I'm not going to be able to do just the black ones, no matter how hard I try. But with this one here, now I'll be able to do just this one right here twice. Let's see if I can do it. So I'm just going to start here, go down there. There's usually lots of ways. Just kind of do something kind of reasonable. Go like this. And now I can go here, and you can see the problem. I can go like this, and now the fact that I drew this one in there, there's my final Euler circuit. So this is called Eulerizing it, Eulerizing it when you repeat whatever number of edges is necessary in order to get an Euler circuit. So in this case, the best you can do is to repeat one of them twice. And so the original one that we had, let me draw it again, is was right here. Okay, and you see, whoops, one more right from there to there. Okay, so you count them. You've got 3 of them here. You've got 3 of them here. You've got 3 of them here. You've got 5 of them here. And here you have 4, and here you have 2. So you got a whole bunch of odd numbers in there, so that's not going to work. So we're not going to be able to do it there, but we can Eulerize it by repeating this one and, say, repeating this one. There you go. And there'd be different ways to Eulerize it. But now with that, I'm repeating those 2 edges. Let's make sure we can do it. Here we go. 1, 2, 3. I kind of like to go around the outside, come back in, like this. Oh, no. What did I do wrong? Oh, I started here. There we go. I started right there. There we go. Yep. Okay, very good. So that's the idea. So that's called an Euler circuit. Okay? And the reason it's called an Euler circuit, if you just finish up with a little bit of history, is because in the town that Euler grew up in, Königsberg, in is that Germany or Russia? I can't remember. But you had a big old river. A big old river, and there was an island in the middle of the river. And then it kind of river split like this, and then you had mainland there again or something like that. And you had, this is the town of Königsberg. See if I can spell it here for you. K umlaut O. Okay, and you had bridges that went to these various islands. Like that. Okay, so this is the river. That's all the river water. Okay, and the people of Königsberg wanted to try to take daily, I don't know, Sunday walks or whatever, make those blue, take little Sunday walks, which would start wherever they wanted to start. Say they wanted to start over on the north side here, and they wanted to take a walk that crossed every bridge exactly once. Okay, so that's what they were after. Can they cross every bridge exactly once? So this is an example, again, of making another graph. We don't need the fact that this is an island and that this is either an island or whatever. All we need the fact is that we're starting here. We've got another point here, and we've got two bridges, two ways to get from there to there. Then you've got this piece of land, this piece of land. Then you've got this piece of land, which is down here, and you've got two bridges that go from here to here. Then you've got another piece of land here, another vertex, and you've got one bridge that goes from there to there. And then you've got one bridge here, you're just walking on land, so not a big deal. You've got a bridge that goes from here to here. And finally, you've got a bridge that goes from here to here. So there's another graph. See that? So there's another example of getting rid of all the extraneous information, and you just got yourself a graph there. And as soon as you have that graph, you realize that it's impossible to do it. Because what did we say? We wanted everything to have an even degree, and we certainly don't have it. 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 1, 2, 3. Goodness, everything has an odd. So, so the question is, it's impossible to do. What could we do to Eulerize it? Okay, so we're going to have to cross some bridges twice. What would be the easiest way to do it? If I 1, 2, 3, 4, 5, if I add 1 right there, that takes care of those two. And then I can't make an edge to go from here to here because there's no bridge that goes from there to there. So I'm going to have to add a bridge from there to there, and then another bridge that goes from there to there. I shouldn't say another bridge, but across it another time. See that? So basically, I'm doing this one twice, and I'm doing this one twice, and I'm doing this one twice. So you're going to need to 1, 2, 3, 4, 5, 6, 7. You're going to have to, looks like you're going to have to cross 3 bridges twice in order to get back home, as long as you want to cross every bridge exactly once. And once you have that, let's go ahead and check it out. Now we should be able to have ourselves a Euler circuit. Go like this. Go down here, back up here, go here, go there, and go there. Oops, and I started right there, and then go back there again. That's where we started. So there it is. So there's a nice example of how graph theory, again, tells you not only that you're going to have to cross a bridge twice, but you're going to have to cross 3 of them, and no way to do anything better. So there you go. That's a quick overview of graph theory, and a lot of people spend their whole PhDs. They spend years studying this stuff, and but you've hit the kind of the most essential information, the most important essential information in these 2 videos. So the authors do a good job with it. Okay, very good. Hope you enjoyed the series.